Okay, cool. Well, thank you guys, everybody, for having me. So this is going to be about time series prediction with neural networks. So using deep learning and all of that, fancy terminology to do something that's been important to every data scientist since the beginning of time, which is trying to predict what's going to happen in the future. And really, a lot of the concepts are the same. Just sometimes the algorithms and the abstraction layers that we're putting our numbers through are different using neural networks versus some traditional time series, but that's about it. I'll get to what I do in a second, but I want to kind of gauge where everybody's at and level of experience. And you're welcome to ask questions as we're moving along. So I've got a lot of material here, but I'd rather just create a dialogue and ask questions as we're going through. And we'll see how much we get through, but the goal isn't necessarily to get to the end of the slide deck, but to have everybody kind of understand and spark a good conversation and questions about this topic. So a couple of things. People that are familiar with just the Python programming language. Everybody. Okay, how about NumPy and multi-dimensional arrays? Beautiful. Keras, TensorFlow, a little bit, or scikit-learn, sklearn, there we go. Okay, so some familiar interfaces there. And then what about just very basic neural network theory and time series? Super cool, we have a really good audience today. Okay, so a little bit about myself. I've been basically doing time series with neural networks for the past 2 years because I created one of the first predictive auto-scaling platforms that was for Amazon Web Services. So I would use online learning. My algorithms continuously learn based on the request patterns that are being thrown at servers in the cloud. And then it makes sure that you provision the right number of resources given anticipated usage, right? So we say, oh, there's a big spike coming in 10 minutes because all of our users come online at 5 p.m. So let's start provisioning servers now in the cloud to make sure we have those resources. So I released one of the first auto-scaling platforms based on that. AWS at reInvent just announced theirs only a couple months after I launched mine. And now I'm going to be focusing on starting to tack it onto Kubernetes and OpenStack platforms where some predictive auto-scaling tools don't yet exist. So what I'll be presenting here today is really a lot of the fundamental learnings that I've gone through in creating these systems. And then just the next step is when you take it online, you have more wild data and quirks that you have to deal with. But the core concepts that I'll talk about here today are the same. And then now I'm starting to launch technology services, so I've been focused purely on product, but around DevOps consulting and Kubernetes and machine learning and AWS. So if you guys do need an extra hand with projects that are coming up in the future, then feel free to grab me later or get in touch with me after the event. Okay, so this is a machine learning overview, and I think we'll be able to step through this pretty quickly given everybody's level of expertise. But the one thing I love, this is one of my favorite XKCD cartoons, which is basically what is machine learning, and it's really taking a bunch of linear algebra and then putting it through this black box and nobody really knows what it is, but you get answers out the other end. And that's what's always kind of funny when I do a machine learning talk, is we end up looking at arrays and data and what goes into the neural network and the feature engineering that happens, not so much the ins and outs of what the neural network is doing as a black box. So we'll open up the box a little bit, but we'll mostly focus on the feature engineering that's required to get good results out of a time series prediction algorithm. Okay, what is time series? Basically, we have a curve, where our x-axis is time, and we have y values, right? We want to say, given the history, historical data, what do we think is going to happen next, right? And a child can basically do time series prediction manually by just completing the line where they think it's going to go, right? But it's another step when you want to have a level of quantitative precision and do it online, running all the time, crunching large numbers. That's where neural networks can really come into play. So some application areas, business intelligence being sort of number one. Will's doing a lot of this, predicting sales. What are my sales going to be like next month? Given a whole range of factors, and market conditions. Smart grids, so we were talking about smart cities. So predicting how much energy people are going to use anticipating that energy usage to start allocating power to one place to another more efficiently. High frequency trading are doing this all the time. They're looking at historical data, stock prices, and market conditions, try to predict what a stock value is going to be and get in and out quickly to take advantage of those trends. And just generally resource optimization. If you have an idea of what the future, what lies in the future, then you can more efficiently allocate resources today. And that's effectively what Contour's been doing all along, is anticipating resource requirements for an application in the cloud and beginning to provision resources ahead of time so you can utilize them more efficiently. Rather than just purely reacting to circumstances, you can anticipate and be more efficient with your resources. So this is sort of peering back the black box a little bit, how neural networks are actually computing and working, right? So in this case, we're just taking a what's called a linear activation function. So neural networks try to learn a function that best describes your data that you're feeding it, right? And the way they do that is they take inputs, okay, and we have our input layer of a neural network, okay? It is applying and tinkering with the weights of those coefficients to derive a function with a weight that's going to best fit your data. And in a nutshell, this is what a neural network's doing, okay? It's taking inputs, right, your x values and like a scalar, for example, in a linear function, playing with those values, trying to fit it to the data and giving you a function back. In a very general sense, that's what a network is doing. And we don't really need to go, I'm not going to go too much further into it than that. But any questions on this so far? No? Good? And then the next one is, as you have more complex data sets, right, you're going to have more values that get inputted into the neural network as input nodes, and then we're going to apply weights to all of them. So we're still looking at what's like a linear function here, but now we're applying weights to each one of our x values, okay, and tinkering with these to define a function that's going to best fit our data. So here you see again, just slightly more complex inputs, but the same kind of output, we're getting some sort of linear function. And the only additional step I could have put here is this would be considered an input layer and an output layer, but where you also, you'll hear about deep learning or dense neural networks. Often there's another layer in the middle here, and pretty much the same is occurring, except we have another series of weights that are being applied and more filters to propagate what are the most effective weights for matching our data, right? So sometimes neural network architectures can get very complex. That's just putting more gates, more information in play to be able to tinker with those weights and find a function that best fits our data. And that's where a lot of the innovation comes from. Deep learning layers as well as from memory. So sometimes neural networks are trained to remember very significant weights and propagate that forward through time. So even as you pile more data on, if there was something very significant, that information won't be lost to the neural network. So ultimately with time series, here's what we're trying to do. And I like to think of neural networks as sort of like a blacksmith. You take an activation function. Many times I actually use for time series a linear activation function, just because even you have crazy curves, they can be approximated by a series of infinite straight lines, right, to fit it. And so a neural network is kind of like a blacksmith. It takes a activation function and it applies weights to that function to hammer it out and try to make it fit your data, right? And as you start moving through time, right, we've basically, with a linear activation function, derived a curve that is the sum of a bunch of little lines and little time series predictions. And then the final little review point is just the idea about supervised learning, which is where we basically have data and we have an idea of what our classes are. So we want to say, hey, neural network, or hey, machine learning algorithm, whatever algorithm you're using, this data represents a dog. This is what a dog looks like. So we know what classes we're trying to predict or what our outcomes are supposed to be and giving it an objective, rather than this is opposed to unsupervised learning like clustering algorithms. We don't know the classes. We're trying to just logically group data by their likeness. And this is going to be a really important factor in time series because we want to frame time series as a supervised learning problem. So we want to know what our classes are and what certain data looks like that represents that class. Questions there? Okay, so this is where we're going to get into important feature before we start talking about individual time series applications is time series as a supervised learning problem. And what we're looking at here is just X values, and we could say these represent timestamps. So this would be the second after the last epoch in 1970. And just raw data are values, so we could say Y represents temperature. Let's say we're looking at weather data. And we need to take our raw X, Y values of timestamp and value and frame it as a supervised problem, where we say the last value went into the next step. So X led to class Y, okay, and then X led to class Y. And you see what we're doing here, and I think I have arrows to show how we can frame this as a supervised learning problem. And if anybody's really paying attention, we're, for now, actually going to discard our timestamps, because with a univariate time series, we can basically, by showing the neural network the order of our data, the ordinal values of the timestamps are basically implied. And so the neural network can learn a sequence by just replacing X values with the previous Y, if that makes sense. Okay, so univariate single-step time series prediction. So this will be kind of like the first category that you'll learn. Basically, we're going to have one variable, okay, and it's going to lead to our class, right? We have one data point, and then that leads to the next data point, etc. And it kind of looks like this. So we have raw data, kind of like I showed you on those tables before, and much of it is going to comprise our training data. Then we have our last data point that we'll be using to predict the next point in the series, or what's going to happen in the future, right? So we say, given a value, we just observed a value of 100, what do we think the next value in the sequence is going to be, right? And remember, we've discarded timestamps, so we're just really looking at the history of previous values of Y. So the training concept is pretty simple, right? We create that supervised data set, and we're creating sort of a sliding window to move along the time. And so notice we're going to have to discard this first one because we don't know what the value of like t of -1 is, for example. So we're going to discard that, and then we have in our sequence, we start framing as a supervised learning problem. Okay, and whoops, I guess I don't have the arrows there. So that's kind of like the previous slide we showed. And then sort of training pseudocode, how you can actually instruct a neural network to learn this kind of time series problem. X is going to be a 3D array of sort of our historical values. So it's going to represent the number of samples. So let's say we have 100 previous values. We're going to say we have 100 samples of information. And it's comprised of one time step each, right? Because we're just doing univariate time series at this point. And finally, the feature, each time step just has one feature, the previous temperature value, the previous temperature read, for example. And then Y is our class. What did this data lead to in the next step? So we start to see the relationship between data being inputted in T of 1 and what it is in T of 2. Make sense so far? Oh, and the last thing I want to show, because this is kind of like the sklearn interface, when we have properly formatted our data of X and Y values, then and we've constructed a neural network model, I'll show you how to do that because I have some code samples, then we're literally going to say basically train the network model to fit X and Y values that we have. That's where it's going to go through and start hammering out the weights to output a function that fits our data as the best fit for our data. So the prediction concept, when we start getting into predicting what's going to happen in the next step, I like to show a table like this and kind of animate the process, right? So we have our training set here saying 80 led to 90 and 90 led to 100, okay? Then we want to predict what's going to happen next, okay? So we're going to take our last y value, it's going to become our x. Okay? And then, for example, in Keras or TensorFlow, then we're going to go back to our model and we're going to say, hey, given we just saw 100, what do we think is going to happen next, right? And we would input that into the model, and it would output a prediction for us of what the next timestamp is going to be. This is probably the hardest piece to implement as an algorithm, working with multi-dimensional arrays. And as you start really increasing the richness of your feature set rather than just single values, operating, kind of making this table happen in NumPy with very, very large feature sets and high dimensionality is probably the most complicated thing. But in a basic nutshell, everybody kind of understands so far, right? So, and then the prediction pseudocode would be something of this nature, right? We have a value, we're going to put it in, say, give us what the next one was. Pretty simple, where we're basically consulting this trained neural network to say, apply the function that we have to x and give us y. So, multi-step prediction. This is where it starts getting a little more complicated, but we're still only going to base our predictions on just the previously observed value, right? But then what we're going to do is we're going to continue to step forward multiple times into the future, right? So basically from this time t, we want to know t plus 1, t plus 2, and t plus 3, right? And so we're basically going to take the same concept. The training is essentially the same, right? Because we're inputting a univariate time series data set into our neural network and training it. But we can get multiple steps out of a series, right? And so now it's just a slightly more complicated version where given 100, we go 1 and emit a prediction. Now we're going to turn around and emit that prediction, or turn that into our x value to emit another one, and so on and so forth, to do a multi-step prediction. And many times you have to be careful and you have to be aware of bias. The more steps you're predicting out, you're injecting a lot more bias and error into the scenario because you're basing predictions on predictions. So let's say, for example, we have a time series data set that goes minute by minute, right? And we want to predict 30 minutes into the future. You may not want to do 30 time steps of this nature into the future because you're going to be continuously feeding bias back into the system, and you're going to get a feedback system. And at some point, some number of steps out, the neural network may just go haywire and go off the rails. So let's say we have a minute granularity in our time step, t of 1, 2, 3, 4, etc. And we want to predict 30 minutes out. You'd want to rethink your feature set that you're putting in. You'd probably want to aggregate that time series model into 30-minute increments, right? So you're only predicting one step further into the future. So that way you don't continuously inject bias into the model. But for example, with Contour, what we try to do is we want to know, we predict out 10 time steps. So what do we think is going to happen each minute for the next 10 minutes? But what we do is we choose the highest value to provision based on. So I want to know a given minute which was going to be the maximum predicted value over the next 10, because that's the time window I need to make sure all the servers are up and running, Bootstrap scripts have executed, and the servers are online. But any farther than that, you want to rethink your time scale and maybe aggregate each time in the series represents 5-minute intervals or 10-minute intervals or 30-minute intervals. So you're not iterating too much like this and injecting bias. Yeah?
How do you measure the bias?
Well, you can start looking at the error that's produced from real data. So you can look at if you're actually doing it on like a test set, you can analyze the error. So let's say I predicted out 10 steps ahead. What's the error on my t plus 10 prediction to the actual value? That would be the best way to do it.
How do you feed that back into your model to minimize the error?
Taking the error and feeding it back into the model, I mean, I would back it up and go earlier, which is you probably want to rethink your modeling of the problem. So reframing your time series into aggregate steps of 10 minutes, 30 minutes, or whatever. because it's going to be hard when you've identified that bias, okay? Because you're predicting out too many time steps ahead. That's really kind of like a feature engineering problem, not so much a learning problem associated with the model. Because in this case, I should say, we're just continuously predicting. We're not necessarily feeding these predictions back into the training of the model. So it hasn't learned anything new. It would be just kind of like a misuse of the model that you've trained, right? So you want to think about your features again. So with multi-step predictions, right, you're going to start iterating. And that's just the important thing that I want to show here is, you want to go out 5 time steps, right? You're going to iterate, say predict, and then you're going to plug it back into your X, okay? And do it again continuously until you get your entire sequence that you're looking to predict outwards. So let's go through this, and then I have some coding examples, and we'll step through. This one gets more fun because multivariate time series is really when you start getting into real applications, right? There's a lot more to predict a future value often than just the one previously observed value. For example, let's say we're trying to predict a sine wave or weather data. We'll probably we'll minimize the error even further and have a more predictive algorithm if we consider a sequence of data leading up to that point, right? And then that also starts to protect you from outliers and so forth, because now we're saying, in order to generate a prediction of t plus 1, let's look at t minus 3, 2, and 1, right? So we're starting to look at a sequence of data to predict our next data point or future data points, right? So given we observed this sequence of numbers, what will the next m values be in the sequence as an example? Right? So now you can start to see where the linear algebra-ness begins to come into play, right? Because now our data set's starting to look a lot different, where we're saying, given this sequence, it leads to this value. Oops. Okay, and I want you to notice the sliding window. Looks like I don't have it on this slide, but 60, 70, 80, 90, 100, okay? And just like we did with our univariate time series, now we're going 70, 80, 90, 100, 110. So do you see the relationship here between the numbers? And this is sort of the sliding window through time that we're utilizing to be able to predict our next values. Does everybody see that? And I think I have a slide here. This is just kind of blowing it up what you're actually would be looking at something like NumPy as far as the arrays that you would be working with to train and fit your data of this nature, right? But still relatively the same from what we were looking at before. So this slide, I think, kind of shows the sliding scale, how we might do with a multi-step prediction with a multivariate time series, right? So we use that to predict the next value. So this would be in the prediction step. And then we created a prediction of P1, okay, and so on and so forth. And once again, see how this bias would be creeping in, because now to predict P of 4, right, 3 out of our 5 data points are not real, right? They were predicted from the model. So you have to be very careful about the relationship between the number of predicted values you're using to generate your next output, where we have only 2 previously observed real values. We've injected this many to achieve it. And so the pseudocode starts to become a little bit more complex, where now we have to start using slices of arrays of X, because we have this sliding scale moving as we're making predictions along the line, right? And let's go through this last. This is just like 2 more slides, and then I'll show you, I actually coded up an example. So at this point, we've done univariate single-step time series. We've done univariate multi-step time series. And we've done multivariate sort of like single-step time series. And throughout this process, right, the order of the data has basically been implied by the order we've been feeding it into a neural network, right? Because we threw away our timestamps. So the neural network generally learns the order of data if it's being fed in an ordered fashion. You can shuffle the inputs if you want, so it doesn't learn that implied ordering. But there's a lot of information that is just encoded into a timestamp, right? especially if you're looking at seasonal trends, any kind of trending data, right? That's going to yield a lot more interesting information. So for example, with Contour, right, a business may have way more traffic around the holiday season if they're a retailer, right? So the month of that data point, that observation, is extremely important to predicting what our next values are going to be. So what's the next value? December 25th. Well, December is a very important piece of data if you're a retailer, for example. So decomposing timestamps into multiple attributes. So what we can actually do is, I did this in Python. I just made a random Unix timestamp, okay, and look at all this extra information that we can actually derive just from our timestamp, the time of the data. And this can instruct our neural networks to learn a lot more about seasonality and trends moving forward in the future, right? And then this would be encoded as one timestamp can be broken up, and you can see the richness of data that we can derive just from a Unix timestamp. And then this would be the actual value of, let's say we're looking at temperature request counts. We have a value of 60. And the other one thing I want to mention is with day, that's something that I usually one-hot encode to really encapsulate weekly trends. So one-hot encoding is where instead of saying day is, let's say it's a Monday, well, let's say it's a Tuesday, we wouldn't want to say the number 2. We may want to, because it's more of a classification. So let's say for Monday, we'd have 1, Tuesday would be 0, 1, Wednesday would be 0, 0, 1, etc., right? So one-hot encoding, that's just a little tidbit there, but it's something to look into. When you have data where you don't necessarily want to apply a relationship between them, I don't want to say that Monday is more important than Tuesday. I want to represent them as a class in and of themselves, the day of the week, which is what I did for Contour. Then one-hot encoding is an option that you want to look into and understand. So when you start really exploding multivariate time series and you decompose your timestamps, so let's say we want to predict the next value based on the 3 previously observed events, right? And we've decomposed our timestamps, right? We have decomposed timestamps and then the value, decomposed timestamps and the value, etc. So this would be like one data point that's fed in to produce a prediction. Does that make sense? So this is where you can, I did this more for like illustrative purposes to show the complexity of the data and how rich you can start getting as you explode the dimensionality in the feature space that you're putting in. You can start to encode a lot more data where you have a sequence of events and each event has a lot of data associated with it, right? And this is where the fun linear algebra stuff comes in. You start stacking arrays on top of each other to achieve this kind of result. So that's more for an illustration to give you an idea of what to do. These types of algorithms I had to work on for a while to actually do this on like a live production scenario. So questions there. I'm going to move into like a coding example if you guys want to move on. Yes.
Do you one-hot include the month also, or and this is just for example?
Yeah, you could. And some of that is just experimental. So usually years you'll want to just keep them as is because you don't know the entire size of your feature set, how long your system's going to be running. But yeah, you could one-hot encode the month as well and see what kind of results it gives you. And that would be a good area to do that for. Yeah.
The one-hot for the second and third line should be different, right? That's not just a copy-paste thing.
Yeah, did I make an error somewhere?
Yeah, like so on the 23rd, it should be different than the 22nd.
Oh, these are sort of like minute-by-minute timestamps.
Oh, okay.
So all of these timestamps were taken from the same day.
Oh, okay.
So this is more like, let's see, this would be year, month, day, hour. Okay, so they've all got the same year, month, day,
Okay.
and then kind of like incrementing by the hour and approximately taking the same measurement on an hourly basis.
I just wanted to clarify, it's day of the week, not day of the month. Is what it
Yeah,
said.
day of the week. Yes, right here. So, and for example, with Contour, I was really mostly concerned with weekly trends. And so really trying to capture weekly trends. You know, some companies, Wednesday is always the most popular day that people hit their platform. So I really wanted this class, day of the week, to be important and have weight in the network. Yeah.
Just with this type of data representation, what regularization techniques have you explored?
Oh yeah, like normalization.
No, regularization. Because just looking at this, it seems like there's going to be a problem with memorization of your data set. You have a unique timestamp. For every unique timestamp, you have a unique output. So how would you stop your neural network from simply memorizing your input data over time?
Well, so there's a couple of ways. One is you can increase the number of epochs, so the number of times that the neural network sees your data. And then the other thing I do is, because sometimes you have a strong trend, and it just latches on to that trend. So I shuffle the data as well when you have timestamps representing each point. So I do that so it doesn't latch on to a particular trend. And I shuffle the inputs and often train over multiple epochs, so it sees all of the data set in a different order multiple times, and then evaluate the error on the training set. And if it's, you know, outside of the boundaries of acceptable, then retrain, or I have to go back to the drawing board and change the model. Does that answer your question?
Somewhat.
Oh, and it also brings up a good point. I should say that neural networks also learn best with values that are between 0 and 1. And so one of the other things I do as a technique is as you're talking about regularization, then normalization. So I often change most of the values, especially the y values, to be between 0 and 1. Just the way the neural network applies weights and so forth, the neural network can more efficiently learn values at that level rather than having, you know, lots of significant digits on the left side of the decimal point. Let's see if I can find, yeah, this is it. So this code sample's up on GitHub. Let's see if I can maximize. So I can just kind of walk through like the different steps, and then it's there if you really want to see how to build sort of a, you know, for example, one of the complicated parts is building that algorithm to create a sliding window and reframing as a supervised data set from the raw data. But basically what I did here is just trying to do time series prediction on a sine wave, right? That's plotted, t are timestamps, and y is just values from like 0 to 10,000. And it's very similar to what I did with contour because the values, I should say, most data sets are periodic, right? Most web services, they get a lot of traffic in the evening when people get out of work, and as people go to bed, you know, the traffic dies off, and you see a lot of periodic daily cycles, right? So I've done a lot of time series prediction on very like highly periodic data sets. So I kind of chose that as a sample for you guys, but a lot cleaner than what you would get in the normal of things. So the configuration, a lot of this is just because I'm just generating a fake data set. So it's just the parameters into the sine wave function, for example. And probably the important thing is what I call look ahead and look back. So look back is how many time steps are we going to use to predict the next value? So we're doing it as like a univariate problem here. And then look ahead, how many timestamps, how many times t do we want to look forward in the sequence, and we're just going to do one. And noisy, I'll just show you this thing later, but we're going to do a clean sine wave, and then we can also do a noisy sine wave, which is going to look more realistic when you're actually dealing with signal processing or periodic data sets in reality. So I created a data generator. Let's see, where am I? Might need to execute this. So created a data generator, and X is literally just timestamp, Unix timestamps from 0 to however many days were the timestamps I want, and they increment in 60-second intervals, right? And then I just, in each cell, I kind of printed out the shape of the NumPy array and a couple of data points just so you can see what the data looks like. So these are our x values, right? 0, 60, 120, etc. Up to 2 days worth of data. So I'm going to run that, and then we need to generate our y data set, which is going to be a 2D array where y equals sine of x, or generally, but I've expanded the sine wave function so we can play with our amplitude and other factors, right? And how high we want to shift that sine wave in the positive direction. So if I run that, and then I run the next one, I'll plot it again. You can see like we've just plotted sine wave. It's got a period of 12 hours, okay, and it's going on for 2 days, right? So that's why you see sort of like 2 peaks, or 4 peaks over 2 days, right? So here comes all the linear algebra-ness that's involved in any kind of data science-y stuff, right? So we're just going to split our raw data into train and test sets, and I just used a split. I split it 50-50. So the training set is about the same size as the test set. And just with rounding, you know, the test set got 1 extra. But that's no big deal. So you can see the shape of our x and y's. And right now we still have x train and y train, for example, as timestamps to the observed value, let's say it's temperature. So this one, if you're interested, would be something to take a look at. But this is the little algorithm to create the window data set or the supervised data set, where we start taking the previous value y as the next value x, right, and frame it as a supervised problem. So it's sort of at this point that we are dumping our timestamps in a univariate time series with implicit ordering, right? So we've dumped all that stuff, and now we have a supervised data set. But I've created and stored that information in new variables just so that we can still access the old timestamps and the old ordering of the data, because we're going to need it later on to plot it. So this is always a tricky thing that tripped me up for a while. When you're inputting your x values into, or your training data into the neural network with Keras, it wants basically a 3-dimensional array. It wants a cube of data, so it knows everything about your data schema that you're inputting. So you're giving it a cube, and the 3 dimensions of the cube are samples, the time steps involved, and the number of features of each time step. So samples, we saw with our training and our test sets, we had about 1,444 samples, each representing 1 time step, right? Because we look at, in a univariate, 1 time step to get the next one, and the number of features is that one and only value in the time step, right? So you'll always need to reshape your data into this 3-dimensional array when dealing with neural networks with Keras. And then to give you an idea of what it looks like, okay, this is what our training window data set or supervised data set is going to look like. And that's just like the graph I showed with the arrows constantly pointing to the next value. So this is just sort of invoking the new neural network, okay? You could define any kind of neural network architecture that you wanted. We could add more dense layers. We could use a different layer here. I'm using what's called an LSTM. This is where memory comes into play. LSTMs tend to work really good on time series data sets. They propagate forward through time interesting things that they've learned, which may have happened much earlier on in the data, but were significant weights. It's just like if you have a personal experience where you really learn something, you don't want to just forget it because you've had a lot of experiences henceforth. So that's kind of the idea behind a LSTM neural network, and they tend to perform best on time series data sets. And I'm using as a loss function mean squared error, you know, kind of basic, and the optimizer. And then we've already got our data processed, so now that we've created a basic model that hasn't been trained, then we're just going to model fit. So we're going to input our x and y's. Here I just did 1 training epoch for time, and we're feeding 1 value in at a time into the neural network to see what's going to happen. But like in reality with contour, epochs is usually 2 or 3. I actually shuffle the data set. Sometimes the neural networks can get biased. If, let's say, the first 50 observations in the series were just flat and linear, the neural network's going to throw everything out and be like, it's all flat and linear, even though there may be more periodic data coming overall. So I usually want to shuffle things up so it doesn't get biased from very early values and throw out all the other weights and everything.
I just wanted to understand the Keras thing and the sequential model.
Oh, I broke something. Yeah, go ahead.
What specifies the number of neurons?
Okay, right here. Yeah, I don't know what the name of the parameter is, but because I just did it implicit, but it would be like, I think it would be something like nodes equals 50. So, and it's the first parameter for Keras. A Keras layer is the number of nodes, neurons in your neural network. So the layer here, this would be like our input layer, okay? And I have 50. You usually want to choose a number that's proportional to the number of inputs that you're having. So actually, since everything else is kind of base 12 because I'm using 60-second time steps, actually 60 would be something that makes sense. It usually just performs a little bit better given that. And then this is a dense layer, so this is one of those middle layers that you can add, and I just have a dense layer with one node, for example. So that's the where you're starting to define your neural network architecture right here. Yeah.
You mentioned online learning earlier.
Yeah.
You're shuffling the data. You retrain your model every single batch of data, or how are you handling the online learning scenario?
Yeah. So online, the way I did it was you train the initial data set on the historical 2 weeks that are available from Amazon, right? And you do that by shuffling the inputs. Then it learns online after that, where each new value that's coming in just gets fed individually. So next minute of data has come up, feed another minute of data into the algorithm. Now, what we've done is we shuffled the original inputs, but now we're online. So we're feeding one input in at a time. So now suddenly we've gone from shuffled to sequential input, right? So the best thing to do is retrain the network in its entirety at some interval. Could be a week, 2 weeks, or whatever, and also storing off some of that historical data. You can also just watch it, so you can watch the errors that it's producing in real life, and if the model seems to be acting haywire, then that would be a good time to retrain. I have a couple of retrain triggers. One is we talked about normalizing values. We want our values to generally be between 0 and 1. So if I see a normalized value, like I've scaled all my values and I have one that's at 5, then I know it's time to about retrain the entire network because the range of possible values in our data set has grown beyond what the original training saw. So normalized values trigger, real life errors are a trigger, as well as just a periodic time to retrain the whole neural network to make sure to avoid something going haywire rather than detecting something's off. So I think I just may have messed up with the model is not defined, but it worked this time. So we're iterating through the data set and generating the prediction of what we need to happen next. This is more like it's iterating through the test set, and for each item in the test set, it's trying to predict what's next. So we're kind of like running a simulation. It's like we're moving forward one time step at a time, and what's going to happen next, and then we can plot out that curve to what the real data set looked like. Trying to think if there's anything else that's useful to mention here. But it's one of those things, you can just go back and look at, and I try to comment everything so it's easy to understand. Right, and then when we plot, you can see that we predicted very accurately because we're only predicting one time step ahead. So the blue is the original, and then you can kind of tell up here, right, that we're overlaid one to the other. The red line being our predictions was able to pretty easily match what our test data set looked like. So this is our training data. So this is what the neural network saw before it made any predictions. And then our test set and our prediction set are overlaid one on top of each other because we're not predicting very far ahead. And the previous value is very deterministic of the next value here. Yeah.
What are you predicting exactly, the parameter of the sign?
We are predicting the y value. So what is the...
Unconstrained?
Say what?
Is it unconstrained? The y value is being predicted unconstrained? Or is it constrained by function?
In this case, it's constrained by a function. So you're not going to see y values in this instance that go above 8,000, if that's what you mean.
Oh, I'm just wondering, is it really reproducing a sign function? Or is it reproducing a parameter for a sign function?
It's reproducing, so the neural network has defined a function that's a close fit. And each time step, it is applying that function. So really what you're looking at, this red line, is really an aggregation of many linear functions, right? Because we took a linear activation function, and it's saying for the next time step, apply that, apply it, apply, right? So we're using sort of a linear model and continuously applying it to contour one curve to another. That's actually where sort of the company name came from. There are other activation functions that you can apply as well.
Is it a one-layer network? Is that 50 just in a row and they receive?
This would be like a 3-layer network because you have the LSTM input layer, we have a dense layer that's in the middle, and then we have the output layer that outputs our function.
How's
Yeah.
it break up to 60?
Sorry?
Like, what's the 60? Is it the middle layer?
The 60 is the input layer.
Okay, where's the dense layer?
The dense layer is right here. So we've declared what we call a sequential neural network model in Keras, and then we're just going to add layers to it. So the first one is going to be our input layer.
Okay.
Then the second one is our dense layer.
Is it default to the size of the input layer?
No, you have to define the parameter, how many nodes you would want in a dense layer.
How many are there?
One.
Just one?
Yeah, I mean, we could choose any number. A lot of that's just experimentation, looking at the relationship in the data set. For example, with one, and I'm very much like on the applied side. You know, I'm take the hacker's approach. So sometimes when I'm trying to find the right parameters, I'll just run hundreds of scenarios, right? Because I have like a testing utility where I can basically, I have a configuration file, and I can define all these parameters for a test, right? And so I'll basically look at all of these. You're more like academic data scientist is probably going to have a better theoretical foundation for choosing what the right number is going to be. I basically will brute force and find those numbers programmatically. And so I've created custom software to find those values.
So to visualize that network, it would be 60 neurons funneled down into one, funneled to
Yeah.
how many output neurons?
The output neurons will be one because it's defining one function.
So 60 to 1 to 1.
Yeah, so the dense layer in this case kind of acts like a gate. So that's something that I found works well with like a univariate time series, right? So I think it's proportional to the feature set, and that's why you're getting better. You're minimizing the error better adding that dense layer, but that's just speculation. That's delving into the black box that I'm less familiar with as well.
And you weren't predicting every single value out, you were predicting one value out?
One value at a time,
Yeah.
right. So I didn't say, here's the training set, now draw me a whole sine wave, right? What I said is we're moving along one step at a time through the test set and predicting just the next value into the future, right? If I tried to have it, like we were talking about, predicting many steps out, you'd want to revise what your time scale is. So to the neural network, you're always predicting, less than 10 steps ahead, right? So you would change your time scale. If we were at t of whatever this is, and we wanted to predict what t is going to be over here, then you'd want to change your time scale and your feature engineering to be more appropriate for that. Oh, and there's one other thing I wanted to do, and we'll just rerun this again. So one thing I did is we can add noise to our signal, and let me try to just rerun everything. So we've added an element of randomness, so we're just going to make a noisy sine wave, adding Gaussian noise, and you can see kind of the relationship there, and we have a little less accuracy just visually looking at it because now we have random values, so there's an element of randomness that's put in. It's less deterministic than the actual sine function, right? This is a lot what the data looks like dealing with auto-scaling and web services. Their request counts, how many HTTP requests that they get, you know, on a minute-by-minute basis tend to look a lot like this. So you basically have a noisy sine wave, and so that's what you're trying to predict. Yeah.
Is the red the prediction?
Yeah, the red is the predicted values, and the blue are the actual values. So, you know, I probably should have graphed the test set with like a green or something, but they're overlaid one on top of the other.
Is there a way to teach the system that if you get such a noisy looking prediction, there's probably noisy data?
Yeah. Well, you can do that with filtering. So just as I have applied Gaussian noise, I'm just randomly toggling the value out of the sine function, you know, by a certain multiplier. I can show you that really quick, and then I can talk about signal filtering, signal processing a little bit. Where I generate my x values, right? I said if noisy, I'm just creating random noise that's sort of like normally distributed, right? And taking our y values and then an array of equal dimensions of just random values and multiplying one by the other to generate that noisy sine wave. So if you need to, in real life, if you want to take that noise out, then you're going to use signal processing libraries. Actually, scikit-learn has some things that you can say. The assumption is if the noise is Gaussian, you can apply a Gaussian noise reduction filter and try to reverse the process that I've just done programmatically. If you have a real-life noisy signal, you can put it through filters in order to take some of that noise out. So you have a cleaner line to train the neural network on, and you have like a cleaner input set to train the neural network on. Does that answer your question?
Yes.
Yeah.
Could you talk about challenges in dividing your train and test data when, you know, in time series have this inherent time dependency that you're modeling? So how do you go about breaking down your overall historical data into chunks that when you test on one part, you know that it's really independent from what you train on?
So, trying to think the way to go about your question. Training and test sets, sort of like in real life. So, basically in real life, I'm going to take the entire historical data set, and that's going to be used as training data, right? And then I'm going to look at the performance of my algorithm against the real data that it's performing against, right? So, for example, I'm taking the entire historical data. This would be online, right? I'm going to input that into the neural network to train it. And then the neural network is running, it's emitting its predictions. I'm going to want to compare its predictions against what the real values are. So I'm always interested in predicting, for example, the number of web requests that are hitting the server. So I'm keeping a log of what my predictions were and what the real values were, and comparing the distance between the two. And if it's outside of acceptable boundaries, I'm going to retrain the neural network. And if it's really bad, then I may even alert, or I fall back to reactive autoscaling to do that. So you need to track basically the performance in an online scenario. That's how you're going to do it. So your test set is just real data after you've trained the neural network, versus when you're modeling, okay, you're taking a sample data set and you're splitting it in two to make that happen. In an online scenario, it's just continuous and fluid, right? So you're looking at it as just one kind of continuous fluid operation that's happening.
So the 60, let's make sure I got the picture right. The 60 inputs to the model, that's the 60 previous samples, essentially? Or?
No, the number of input layers is basically the number of parameters or weights in the polynomial that we're going to be trying to hammer out, right? And it usually you want it to be proportional to the shape of your data or the number of samples that you're putting into it, right? So that's going to basically say how many hammers the blacksmith is using on the anvil.
What you're saying is actually just sort of builds a piecewise linear approximation? That's what's happening?
Yes.
This was the univariate. This wasn't an array as input, or is this the array?
This was the univariate case. So, but it's still programmed that I haven't tested it, but I should be able to increase the look back and it should work. Like for the case with contour, I actually got the best performance with a look back of 20. So to predict a given y, I would look at a sequence of the previous 20 events that happened, right?
So it's difficult to judge the performance of the model on the noisy data just by looking at the visual representation.
Yeah.
I don't know if you have any loss metrics on the noisy data, but
I should have
just looking at
printed
the
the history.
picture, it makes me wonder if maybe the model is just memorizing the noise in the original test training data set and reproducing that noise in the test data set. And it seems like just memorizing the sine function will give you better performance on average than reproducing the noise from the
Yeah, actually, I'm less familiar with it, but I believe it's Fourier series is based on sine waves. And that's another technique that's like yielded pretty accurate results. So I'm trying to think.
Yeah, I'm just trying to understand the loss in the previous model without the noise versus the loss in this case.
Yeah, it'd be nice. I wish I could do a side by side actually, or we could rerun it again. But yeah, in some cases it can just learn the noise pattern. Here it's normally distributed, so it knows certain noise values are going to appear more than others, and it starts to find that. So yeah, it's very much a possibility. Generally, even in real life, I found that it works well, and you'll see it'll get the gist of the curve. So yeah, this is something that I've gone with. Yeah.
Because you're only predicting one step ahead, you're not really predicting the curve, right?
Right.
Yeah,
Yeah,
you would have to run it over a longer time series to get.
Yeah, you have to run it over a longer time.
It's actually picking up the seasonal
Yeah.
patterns.
In this case, because I'm using a linear activation function, it's not learning a sine wave, right? What it's learning is basically a linear relationship between values of x and a value of y. So it's always applying a linear function to get from one step, so previous data, to the prediction in this case. So this is really the aggregation of 1,440 lines, linear functions between one to the other. So that's how this neural network has learned to connect x and y, is a linear function. But we could use a different activation function like tanh or ReLU or something like that. And like with my testing platform, that's what I've done as well, is I've parameterized the input or the activation function, but I've gotten the best results on linear. And I think that's maybe because of sometimes the noisiness and randomness of the data set. The linear function tends to not go so far out of bounds that another activation function might.
But this is an LSTM neuron.
Yes. So, but what it's learning is a linear function, a linear relationship between the data points. So, and that's one area, and then there's a lot of research that I know goes into that area, the right activation functions for different application areas. But yeah, linear worked well in my case. Otherwise, it'd be hard to pull up, but when we saw the linear, the neural network diagrams in the very beginning, with the input and the output, or the output was just the linear function. If you were applying like a tanh or a ReLU or something like that, it would be the tanh of the linear function, right? That it would output as a function from the neural network. Anybody else? Yeah.
Did you try other time series methods before jumping to the neural nets, like ARIMA or something?
Yeah, I did, for example, linear regressions. I did, I'm trying to think, Fourier series. I was even doing kind of like a Gaussian regression, which basically just assumes, the next point is going to be somewhere within a normally distributed array of values and picking the most likely one. I did a couple of other different neural networks. LSTM performed the best on my test data sets. So I went through all of that. What's interesting, around the same time that I started this experimentation, Google was doing the exact same thing, except they were looking at the whole internet, and they were looking at the amount of network traffic. And they came to very similar conclusions where my data set worked best with the LSTM. Theirs worked best with their cousin, which was it was like a deep recurrent neural network. Just the memory propagation works a little bit different in that algorithm. And they went through the same process, and since they were looking at periodic data, their hypothesis was that the Fourier series might actually perform the best because it's based on sinusoidal functions or periodic functions. But the neural network seems to pick up on some other interesting trends in the data that helps it minimize the error a little bit better than some of the classical machine learning models. Cool. Anybody else? Awesome. Well, guys, thank you very much. Be hanging out for a while and gonna go to Harp and Kelp, so feel free to hang. Let's get some beers.
Thank you, Scott.
Yep, appreciate it, guys.
Thank you, everybody, for coming. Next month, January, we're going to have Greg presenting a session on generative adversarial networks, or GANs. Promises to be quite interesting. We're going to the pub in the corner, the Scott and the Harp. So please join us.